This lecture is about parallel operation of generators. So we look at the requirements, the reasons behind why we operate generators in parallel, as well as any possible, say, the requirements, then means by which we measure, or before we parallel generators, what we are supposed to do, the characteristics of generators when they are operating both alone and in parallel with other similar generators, as well as the dynamics of operations within a large system. And we'll do one or two examples of the same. So let's get started. Right, so when we have a set of generators, there are certain advantages to operating them in parallel. So operating them in parallel would mean that you have more than one generator in the same area, two or more, that you would be able to link together and be connected to the same set of loads. So the advantages of this type of setup would be, first of all, a greater load can be supplied. Obviously, if you have a 10 MVA load, you can supply it with a series of 1 MVA generators. Secondly, you can have greater reliability of the system. This means that if any one generator would fail, you are likely to be able to still manage to supply at least some of the load because of the other generators that are connected. Whereas if you only have one generator, you will only be able to supply as long as that generator is functional. If it goes down or if it has any issue, you would not be able to supply the load. And that leads us to the third one, which is the ability to maintain. So maintenance is possible while the generators are running. So again, if you have a bank of 10 generators and you need to pull one out for maintenance, depending on your load, the rest of the generators would be able to run continuously. You do not have to disconnect your loads in order to serve maintenance. And another advantage is the ability to manage supply and efficiency. This is to say that all generators that are in this type of situation you would only run those generators which are needed for the load. So like if your load is variable or it varies with time, you would only switch in generators as they are required. So what are the requirements in order to connect generators in parallel? So there are a number of requirements in order to have your generators running together, connected to the same load in parallel with each other. Firstly, the phase sequence must be the same, right? Phase sequence means the order in which the red, yellow, and blue phases reach their peaks must be the same for the system that you're connecting to and for the generator that you wish to connect to that system. They must be running in the same order. So if your system that you're connecting to is red, yellow, blue, your generator that is coming in needs to also be red, yellow, blue. If it is opposite, there will be currents flowing in between the generator and the system instead of going directly to the load. Secondly, terminal voltage must be nearly the same. So if your generators are running at 11 kV, it should be approximately that voltage. So if the system voltage is 11 kV, your generator should be operating at close to that. This will allow it to match up with the system when it actually joins. And number 3, the frequency must also be nearly the same. And number 4, there must be no phase difference, right? So the phases between them, that is the power angle or power factor, should be the same with the system that you wish to connect to. So at this point, it would be useful to introduce the concept of an infinite bus bar, or to remind you of the concept of infinite bus bar. So this is defined as a three-phase supply with a constant voltage and frequency, regardless of the loads that are exchanged. So it's a three-phase system. This is because you have systems that have so many supply generators and so many loads that the voltage and frequency are extremely stable, such that the addition of one more generator would not make a difference to the voltage and the frequency. As we will see going forward, you remember we talked about voltage regulation. That is when a generator is supplying a load. If the load increases, there's a tendency for the voltage to dip. So in the case of an infinite bus bar, your generator, if you connect a generator to that system, or even if you connect a load to that system, the system is so large that it will not be affected in terms of voltage and frequency. You can supply or demand as much as you wish from that system. The other concept that we want to introduce is synchronization. So synchronization is the adjustment of the speed and frequency of a generator when it is being connected to a system. So in order to achieve synchronization, you need to meet all the requirements that we have listed here. So when all these requirements are met, the generator is said to be synchronized to the system that you want to connect it to. Okay, so what are the conditions for synchronization? We've listed them here. You need to have the phase sequence to be the same. The terminal voltage must be close. Frequency must also be close. And the phase difference, the power factor, should be roughly the same. It should be close enough so that they are not too far divergent from each other. So how do we identify if a generator has the right phase sequence, first of all, for connecting it to another load? So let's take this illustration. So you have generator 1 supplying a load, and you want to connect generator 2 through switch S1. So we assume S1 is connected together so that it switches at once. And you want to check what is the phase sequence, or is it possible to connect to that system. So your system consists of generator 1 and the load, and your generator that you wish to connect is generator 2. Now we would have the setup as indicated here. So you'd have lamps. These are lamps connected across the switch. So one, and I call it a leg of the lamp, would be connected to the system voltage, and the other would be connected to the generator voltage. The assumption, of course, is that your generator is running at the required frequency and voltage and ready to go. But you just need to check the phase sequence of what is there. So how would we go about this? If the phase sequence is opposite, so like assuming this phase sequence is red, yellow, and blue. If the phase sequence was red, blue, yellow, which is the opposite of the phase sequence, these lamps would light up out of sync with each other. So they would go bright and dim in different instances, right? So if lamp 1 is bright, lamp 2 might be off, lamp 3 might be a bit dim, and so on. So in order for you to ensure that they are in the same phase sequence, the red, yellow, and blue, you would exchange 2 terminals, either of any 2 of the 3 terminals. You exchange them so that you now have a correct sequence that matches. So if you have a correct sequence that matches, you will see that the 3 lamps will light up and dim together. Now the lighting up and dimming is not due to the peaks and troughs of the sequence itself. The lighting up and dimming is because if we take, for example, the phasors of the system, say generator 1, the system generator 1, if those are the phasors, which is red, yellow, and blue, your generator 2 would be in a similar way, because they are connected in 120 degrees opposite to each other. So R, Y, and B. We've already assumed they're in the same phase sequence, so they match each other in terms of the phases that they have. So if you were to superimpose the phasors of each of those, assuming 120 degrees all across, the direction of rotation, the phase angle of generator 2 may be slightly faster or slightly slower than the existing generator 1 phase angle. That would mean, in terms of the phasors, it would appear that if we assume generator 1 as the baseline, it would appear that either generator 2's phasor is moving away from generator 1 or it is moving slightly towards it. So if it is faster, it is moving away, say in an anti-clockwise direction. If it is slower, it is moving towards it, say in a clockwise direction. And it is that difference, because if you look at this circuit, this is the equivalent of your red from the main circuit, and this is your red phase from the generator 2 circuit. So your lamp is connected across these two, right? And your lamp here is also connected across these two and across those two. So what the lamps are actually showing is the phase difference between the two. So as long as there's a phase difference between the two, there will be some voltage circulating between them. So the aim of checking the phase sequence is to ensure that you can see that brightness or dimming going in the same sequence, right? So let's look at it a bit more in terms of proper synchronization. So when you have synchronization, now we have a slightly different setup, still with 3 lamps, but you can see they have been set up slightly differently. So this illustration shows the wiring for a setup which we want to connect to. So let's say you have, this is our generator 1, let's call this infinite bus bars, and it is part of a system that you want to connect to, and you want your generator 2 to connect to your system of infinite bus bars with your generator 1 already running. So in this case, you now have what we have shown. So if this is the phasor of your infinite bus bar in red, right? Your infinite bus bar, which has a generator 1, is in red color over there. And the incoming generator, generator 2, the phasor is in the blue color that we are seeing there. So what you're seeing is the phase sequences are matching each other. So red to red, blue to blue, and yellow to yellow. And blue, and the incoming generator seems to be slightly ahead of the infinite bus bar, right? So there's a phase difference in between the two. So now if we look at how the lamps have been wired, so you have this lamp 1 is connected between the red of the infinite bus bar and the red of the incoming generator. So lamp 1 is in between the two like that, right? Then you have lamp 2, which is connected between the yellow of the infinite and the blue of the incomer. So yellow of the infinite and the blue of the incomer. So it is lamp 2. Okay. Then you have lamp 3, which is connected between the blue, which is there, and the yellow. So it goes through here to the yellow, right? So you have lamp 3. So you have those 3 lamps connected in that phase sequence. Now, we said that the incoming generator is either slightly faster or slightly slower in terms of the phase angle than the infinite bus bar that it is going towards. Okay, so it will either be slightly faster or slightly slower. So it's tending to go backwards or to go forward, clockwise or anti-clockwise. In this case, lamp 1, if we have the, let's just pick one. So we pick one that is We are moving forward, right? So it means that all these phases, the blue ones, that is the incoming generator, the ones that are colored blue, are all tending away from their counterparts within the infinite bus bar. So red in the incoming is faster than red in infinite. Blue in the incoming is faster than blue in infinite, and so on and so forth. So what that means is, as long as there's a gap between the two, there's a voltage between each of them. What will be seen in lamp 1 is that it will start off as dark and go towards bright. All right. So if in the initial sequence it was nearer to red, the incomer here is nearer to the infinite, it tends to move away from it. So the difference in voltages between the two is increasing, meaning the lamp is getting brighter. The lamp indicates visually the potential difference between the 2 points where it is connected. In the case of lamp 2, we now have it is getting dimmer from maximum. So initially it is far away from the yellow, yeah, but because the incomer is moving towards it, so it appears to be reducing the potential difference between the two. So it is from a maximum brightness to dim, right? And then L3 will be, it is brighter and even becoming more bright because it is moving away from its counterpart. Okay, so bright to brighter. All right, so those will be the sequences. So it will start at the instant before this moment that is depicted here. They will be as indicated, and then they will tend to move brighter, or the lamps will become brighter or dimmer according to the sequence that is indicated. When we have achieved synchronization, we will be able to note that the difference, this speed of angle, the movement away from each other between the incoming phase and the infinite bus bar, you will have matched them so that these will remain stationary. So the idea would be to match them such that there is no phase angle between them. All right, you would want to match them at the point whereby they have rotated, and the red, this red in the incomer, is matching the red at the infinite bus bar. So you would want to tend to have it moving at that point. And at that point, when it has reached, of course, you will find that lamp number 1 will go off, and then lamps 3 and 2 will be fully bright at the same brightness. Okay, so at the moment of synchronization, lamp 1 is off, and lamp 2 and 3 are at same brightness. Okay. Now, of course, this poses the problem that how would we be able to note that? How do we fully indicate? Now, this was a system that was in use. It's a fairly easy system to put in place, so you would run into it in some places. But nowadays, of course, in the area of digitalization and so on and so forth, generally what you would find is a machine called a synchroscope that automates this process. We won't go into how it operates. Synchroscope is a meter or some kind of indicator instrument that literally shows you if your generator is fast or slow, and you would need to either slow it down or speed it up to match the positions of the infinite bus bar that you want to connect to. Synchronization, of course, involves speeding up or slowing down the generator's prime mover so that it is matching the speed and frequency of the bus bars.